If you attempt to force complex, highly structured enterprise documents through a traditional RAG pipeline, the entire system breaks. The standard architecture operates on a strict one-way street. The user queries, the database retrieves, and the LLM generates an answer. That linear path fails the moment a prompt requires multi-step logic or pivoting based on newly discovered information. Worse, the way these systems process data, slicing documents into arbitrary token-sized chunks, destroys the logical architecture of the original text. To scale AI for actual enterprise use cases, engineers have to abandon this passive pipeline model altogether. Building a production-ready system requires two distinct architectural upgrades. First, we upgrade the control flow. Second, we replace the underlying data structure. We start by moving the control flow away from a passive sequence and into an agentic loop. This grants the large language model the autonomy to interact with retrieval mechanisms, not as a forced step, but as discrete tools it can choose to use. Next, we abandon vector embeddings entirely. Instead, we map the document using hierarchical tree indices, an architecture known as vectorless RAG. Solving the enterprise context problem requires mastering both sides of this equation, how the agent acts, and exactly how the data it reads is structured. Let's examine the traditional RAG pipeline. The flow of data is entirely predetermined by the code. In that setup, the LLM sits at the very end of the line, acting merely as a summarization engine for whatever text the database spits out. By repositioning the LLM as an autonomous router at the center of the architecture, we hand over the steering wheel. This is the REACT framework. It operates on three continuous pillars: reason, act, and observe. In the reason phase, the agent actively analyzes the user's query to determine exactly what context is missing before it makes a move. Then it enters the act phase. The agent dynamically calls a specific discrete tool to find that missing data, whether that's a vector store, a web search, or an internal API. Finally, in the observe phase, the agent evaluates the retrieved data. It decides if it has enough context to answer the prompt, or if it needs to initiate another search loop. Granting the LLM autonomous tool use transforms retrieval from a static pipeline into an iterative, dynamic reasoning engine. But an intelligent agent is only as good as the data it retrieves, and that exposes the core weakness of vector databases: token-based semantic chunking. Vector databases ingest text by blindly slicing it based on character counts, completely ignoring the meaning of the layout. This arbitrary slicing severs crucial headers. It separates chapters and fractures logical boundaries. Imagine an agent querying a dense 50-page annual financial report, looking for indicators of corporate stability. Because of how cosine similarity matches data, the database might retrieve one disjointed chunk from page 22 and another from page 40, simply because they share keyword overlap. Those isolated chunks are stripped of the surrounding structural context the LLM requires to analyze them accurately.
It sees the text, but it has no idea what section of the report that text belongs to. Semantic chunking destroys the connective tissue of professional documents. When the agent tries to reason over fragments, hallucination is inevitable. The structural solution to this is vectorless RAG, an approach that relies entirely on hierarchical tree indexes. Think about how a human expert navigates a massive textbook. They don't read every word looking for a key word. They consult the table of contents. We replicate that process by first parsing a raw document to extract its existing headers and distinct logical boundaries. Every detected header maps to a distinct interconnected node. If a document lacks a native table of contents, we deploy an LLM to read the pages and infer the heading structure automatically. Next is the summarization phase. Rather than embedding raw text chunks into a database, an LLM reads each detected logical section. The LLM generates a localized, highly specific summary exclusively for that exact section of text, storing it in a JSON format alongside the node ID and page range. These individual node summaries are then compiled into a comprehensive JSON tree index. The document's entire architectural map has now been captured perfectly without generating a single vector embedding. At the inference stage, here is how a user's query is executed using this new JSON tree index. The agent receives the user's prompt, and we pass the entire JSON tree directly into its context window. The agent utilizes its React loop to logically reason over the top-level JSON summaries, bypassing the need to query a vector space. By analyzing those summaries, it deduces which specific subnode contains the required information. During the extraction phase, the agent uses the chosen node's metadata to pinpoint the exact page range. It retrieves the raw, uncut text from that section, preserving all original formatting, tables, and surrounding context. In the final step, the agent formulates its response strictly using this structurally intact text. Traversing the JSON tree preserves flawless document context and completely eliminates the unpredictable guesswork of cosine similarity. Vectorless RAG is an intentional engineering choice. It is a powerful tool, but it is not a universal solution. The primary performance cost is time. Requiring the LLM to traverse a JSON tree and read summaries at inference significantly increases latency. There is also a financial cost. Parsing trees and conducting multiple reasoning loops per query drastically increases token expenditure. This chart shows a decision matrix for choosing your system architecture based on your dataset characteristics. Deploy traditional vector RAG for high-scale heterogeneous datasets, where sub-second latency is critical. Deploy agentic vectorless RAG for complex structured documents, where structural reasoning and accuracy are paramount. Ultimately, the most robust enterprise architectures will be hybrid. They will deploy intelligent routing to leverage vector search for scale and tree traversal for precision.